I will be working the problems from 2.3. I will start with number 1. We have f of x equals 2 to the 40th power, and we're asked to differentiate the function. No work to be done here. 2 to the 40th power is a constant, and we know that the derivative of a constant is always going to be 0. So remember that if c is, we have a constant c, the derivative of it is always 0. This is a constant, so f prime of x will be 0. Number 2, exactly the same, pi squared, that's a constant, so derivative is 0. So let's move on to number 3, a little more interesting. We have f of t is 2 minus 2/3 t. F of t, 2 minus 2/3 t. All right, now we get to start using some of the rules here. So we have a function that is the difference of two functions. You can look at that as its own function. This is its own function. And so the rules of differentiation allow us to take the derivative of each one. So this derivative will be equal to the derivative of 2, whatever that is, minus the derivative of 2/3 t. Now the derivative of 2, because 2 is a constant, is 0. And then minus, now over here, I have a constant times the function, right? A constant times a function. Whenever we have that, that constant will just come along for the ride, and then all we have to do is take the derivative of what the function is, in this case, the derivative of t. And the derivative of t is 1. That's just something we should know. Derivative of x is 1. But the reason why is because we start with t to the first power. That's t. When we take the derivative of it, we move the power out, 1. Then we have t, and then we subtract 1 from the power, 1 minus 1. This gives us 1 times t to the 0, and t to the 0 is 1. So we get 1 times 1, that's 1. So we should get 0 minus 2/3 times 1, which should just be negative 2/3. And if you think about this a little bit, the derivative, remember, was the slope of the tangent line, and this function is a linear function. This looks like y equals mx plus b. So the slope of this line is this, negative 2/3, and so if you're on that line, the slope is negative 2/3, go to any point, the tangent line will also be negative 2/3. We'll have a slope of negative 2/3, which is what we're saying here. So it matches up with what we would think would happen. All right. Number 4, f of x equals 3/4 times x to the 8th. Capital F of x equals 3/4 times x to the 8th. So the derivative of capital F, well, we have a constant again times a function, so that's just going to come along for the ride, times the derivative of x to the 8th. And now I'm going to use that rule again, that if I'm trying to take the derivative of x to the 8th, the 8's going to come down in front. I'll have x to the 8 take away 1, that's 8x to the 7th. So this will become 3/4 times 8x to the 7th, and then of course 4 goes into 8 twice, so we'll just have 6x to the 7th. There we go. Number 7. Wait a minute, hold on. Yeah, number 7. Number 7 is f of x is 3x squared minus 2 cosine x. Am I doing the right one? Oops, sorry. I knew I was missing something. What about 6? Okay, f of t equals 1.4 t to the fifth minus 2.5 t to the second plus 6.7. We're asked to differentiate the function. So we're going to try to find the derivative using the shortcuts. All right, so I have 1, 2, 3 terms. I can differentiate each one separately. The 1.4 comes along for the ride because it is a constant attached to a function through multiplication. I will need to take the derivative of t to the fifth. Minus 2.5 times t squared, so the minus 2.5 comes along for the ride. I'll need to take the derivative of t squared, and then plus the derivative of a constant, which I know is going to be 0. I forgot my prime. All right, so the derivative of this, okay, I'm going to have 1.4 here. The derivative of this, the 5 comes down in front, and then we subtract 1 from 5 and get 4. Then we have minus 2.5, and then same thing here. 2 comes down in front times 2. T to the, subtract 1 from that power, we get 1, so just t. And then derivative of this constant is 0. We don't need to write it, I'm just putting it there. So now we need to multiply, clean this up a little bit. 1.4 times 5, that's 5.4, I believe that's 7. 7t to the fourth. And then 2 times 2.5, that's going to be minus 5t, and then plus 0, so that's it right there. Okay, moving along to number 7. F of x equals, what was it, 2x? 3x squared minus 2 cosine x. All right, 2 terms. So I can do the derivative by just doing the derivative of each one. I have a product right here, constant times the function, so the constant comes along. I'm going to take the derivative of x squared. And then I have another constant times a function, so minus 2 comes along, and I need to take derivative of cosine x. So this just becomes 3, and then derivative of that is 2x, and then minus 2, and then the derivative of cosine of x, which we talk about in class, is negative sine x. And now we can clean up a little bit. We have 3 times 2 is 6, so 6x. And then we have a negative 2 times a negative sine x. Negative times negative is positive, so I'll put plus 2 sine x. That's it. Number 8. Y equals sine t plus pi cosine t. All right, so I want the derivative, so my notation's a little different here. Derivative of this, I write y prime equals, and I have 2 terms, I can do them separately. The derivative of sine of t, whatever that is, plus pi times a function of t, so pi comes along, and then I need to take derivative of cosine t. Derivative of sine of t is cosine t plus pi, and then derivative of cosine t is negative sine t, and that means cosine t, and then we're adding, but this is going to multiply to be a negative, so it's going to turn to subtraction, minus pi sine t. Done. All right, pretty straightforward so far. Okay, number 9, x squared times 1 minus 2x. F, what is it? G of t. G of x. X squared. My brain is not turned on yet. It's Friday morning. It's like 8 o'clock in the morning. So I apologize ahead of time. All right, we want to find the derivative. So we want to know g prime of x. Now, This problem is different than anything we've seen so far because I have a product, right, of a function of x times another function of x. And the big mistake that people make is they just say, okay, I'll just take the derivative of this and then take derivative of this and just put the answers and multiply them. That is not correct. We actually will tackle that in the next section. How do you deal with products? But because this is a pretty easy multiplication to do, we'll just distribute through first. This will give us x squared and then minus 2x cubed. Now we don't have the product anymore. We have two terms and we can just take the derivative of each one. So I'm going to start moving a little faster, okay, because you've probably, hopefully, picked up on this. The derivative of this one, the 2 comes out, we just get 2x. And then the minus 2 comes for the ride. And the derivative of x cubed is 3x squared. So just clean it up. 2x minus 6, 2 times 3, right? X squared. There you go. That's it. But you have to do this distribution right now. In the next section, we'll be able to deal with it, just like I said. We'll be able to do that without having to do this. And that will be the product rule, but we're just not there yet. All right, let's look at 11. G of t is 2t to the negative 3/4. All right, well, pretty straightforward in terms of, it's just a single term, so I can take the derivative pretty simply. 2 is a constant attached to a function, so it'll come for the ride. And now I need to take the derivative of t to the negative 3/4. I need that derivative, so I'm going to do that right here. All right, so negative 3/4 is the power, it comes out in front. Then I take t, and then I take the negative 3/4, and I subtract 1. And to do that subtraction up there in the exponent, I need a common denominator. So I look at this as being a 1 over 1, and then get a common denominator of 4. So it's negative 3/4 minus 4 over 4. And that becomes negative 3/4 t to the, when we subtract these, we get negative 7/4. And that's it. So we come back here, we've got 2, and then we have times negative 3/4, and then t to the negative 7/4. And I can put these two together, multiplying this, I get negative 6 over 4, it reduces, so you get negative 3 over 2, negative 3 halves, t to the negative 7/4. And it's perfectly fine to leave that answer like that, but you can also use the fact that t to the negative 7/4 is the same as 1 over t to the positive 7/4. That's just from algebra, rules of exponents. And you can just multiply straight across now, and this would become negative 3 over the 2 times this, so 2t to the 7/4. We just need to be comfortable going from here to here, and if we had to go backwards, here to here. So that's correct, and so is that. All right, number 12, cy to the negative 6. b of y equals cy to the negative 6. This is number 12. All right, so it's important for us to understand here that the variable, the independent variable in the problem is y. Then we have this c here. What's that? Well, that's just some constant. They're just not telling us what it is. So we'll treat it like a constant. When we take the derivative, since this is a constant times some function of y, it'll come for the ride. Then I'll say times the derivative of y to the 6, negative 6. And to do that, y to the negative 6, the negative 6 comes out, so I'm going to put negative 6 here. Then y to the negative 6 minus 1. So I have to subtract 1 from negative 6. Be careful there. That's, let me put these two together. That's a constant times negative 6. That's just negative 6 times that constant, whatever it is. Y to the negative 7. That's correct. You can leave it like that. Or you could write this. So what I did was I rewrote this as 1 over y to the 7th, and then I put them together and I got this. Where am I at? 13. Capital A of S equals negative 12, or negative 12 over S to the 5th power. Negative 12 over S to the 5th power. All right, well, you can make this hard or you can make it easy. Let's see. All I'm going to do is use properties of exponents first to get this back to a single line instead of a fraction. Because right now, up to this point, we don't know how to deal with taking the derivatives of fractions, or what we call quotients. We will have a rule for that later. But for this, we can just say this is the same as negative 12 s to the negative 5. So just rewrite it first. And then when you come to take the derivative, we have product here between a constant times a function of s. So the constant comes along, negative 12, times, now the derivative of s to the negative 5, the negative 5 comes out, so I've got negative 5 here. S to the, well, I take negative 5 and I subtract 1, I get negative 6. So this is negative 6. And then I put those two together, 50, 60, I think, 60, my goodness. S to the negative 6, which is correct. I could also write 60 over s to the 6th. Either one of those is fine. So again, dropping it down, just get used to it. All right, number 15. 3a plus 1 squared. Capital R of a equals 3a plus 1 squared. This is number 15. So here, what I'm going to do is realize that I actually have a product here of two things. So this squared is the same as 3a plus 1 times 3a plus 1. Now we have to do it this way. Later on we'll have a shorter way of doing it. But for now, the best we can do is take derivatives of our variable to powers, like x to the 5th, x to the negative 5. Something like that. But when we have something complicated like a binomial that's being squared, we can't just take the derivative of each one. It's not that simple. So I'm going to do this first, and then I'm going to FOIL. So I'm not doing any derivative yet. I'm just cleaning this up algebraically. This is 9a squared plus 6a plus 1. So that's an equivalent statement or expression. And now this is 3 terms, and I can differentiate each one term by term. So I'll go quick through this one. All right, 9 is going to come along for the ride. Derivative of a squared is 2a. 9 times 2 is 18. So 18a. Here, derivative of 6 times a, well, cover up the 6. It's going to come for the ride. Derivative of a is 1. So it's just going to be plus 6. And then derivative of a constant is 0. So that's it. 17, root p minus p. S of p equals root p minus p. All right, well that's 2 terms. I can take derivative of each one. But the rule that we're working with, this power rule, says x to the n, or like our variable to the n power. So I'm going to first convert that root p to p to the 1/2 minus p, like that. Then I'll take the derivative. So s prime of p equals, now be careful on this one. The 1/2 is going to come down. So here's our 1/2. P, and then we're going to take 1/2 and we're going to subtract 1 from it. Now here, I can cover up the minus and ignore it for now. Derivative of p is the same as saying like the derivative of x, so that's just 1. And you have to figure this out. So you get a common denominator, 1/2 minus 2 over 2, that's negative 1/2. And we will have 1/2 p to the negative 1/2 minus 1. Now, if you wanted to, you could rewrite this because it's a negative exponent. You could drop it down to the bottom. It would join up with the 2 down there. You get 2p to the 1/2 minus 1. And then you could go back and remember that p to the 1/2 is a square root. So you could write 1 over 2 square root of p minus 1. And that would be your final answer. Now, in class, I know for sure, I tell you that, look, square root, you just need to know the derivative of. So let me remind you, in class, I'm sure I'm going to tell you, the square root, if you're going to take derivative of the square root of x, this is equal to 1 over 2 root x. You just put that into the memory banks. It happens so much. It's just faster if you do this than if you go and you convert it to half and then do all this stuff and go back and eventually get to this. Just memorize this one. So I could have just said, look, derivative square root of p is 1 over 2 root p. 1 over 2 root p, and just be done. All right, I'm already tired of doing problems. 19. Y equals x squared plus 4x plus 3 all over root x. All right, now we finally have an interesting problem. Because this one, we cannot do, I mean, the temptation here is just to say, hey, if I want to take derivative, I'll just do derivative of that, derivative of that, derivative of that, and I'll divide it by the derivative of that. That is not the way it works, unfortunately. So our only hope is to try and make these, powers of x all on one line without the fraction, which I can do if I just remember what these things mean. So the bottom, remember, is x to the half, like that. And because I have a single denominator in 3 terms up top, I can split this up into 3 fractions. Now, again, I'm not doing any of the calculus yet. I'm just doing algebra. Trying to get x to the n, right? I'm trying to get these x to the n, but without the fraction, without the big fraction. So all of these somehow need to be looked at as powers of x. So properties of exponents, what you'll do here is you'll do x to the this power minus this power. So 2 minus a half. This will become plus, this 4 is just here, and then this is a 1 up there. So you get x to the 1 minus a half. And then this last one, I don't have an x on top. So what I'm going to do is just push that one up. So I have the 3 there. When the x goes up, it becomes negative, becomes raised to the negative 1/2. So we're just going backwards. Instead of dropping it down, we're pushing it back up. Now we have like x to a power, x to a power, x to a power, and that we can differentiate. So let me do this. You have to get a common denominator here. So you turn this 2 over 1 into a 4 over 2, then subtract, you get 3 halves. Plus 4, this one, 1 minus a half is a half, and then plus 3, and then x to the negative 1/2. So I'm ready now to take the derivative. So here it comes. Y prime equals. All right, so here I'm going to do, the 3 halves going to pop out, 3 halves, x to the 3 halves, take away 1. Okay, I'll do that in a second, plus 4. Okay, and now going to bring the 1/2 out in front, so times a half, x to the 1/2, take away 1. By the way, you may notice that's the square root of x, but I'm doing it kind of the longer way here. This one right here, we have the plus 3, and then x to the negative 1/2, take away 1. So I need to do some fraction subtraction up here. And I should be there at the answer. So 3 halves, x to the 3 halves minus 1, that should give you 1/2. Plus 4 times a half is 2. X to the 1/2 take away 1 is negative 1/2. And then plus 3, wait a minute, did I bring out the 1/2? I didn't bring out the 1/2. Why didn't I bring out I was supposed to bring out the negative 1/2. glad I caught that. When I take derivative here, the negative 1/2 comes out, then x to the negative 1/2 minus 1. My apologies. That's that last one right there. So when I do the 3 times the negative 1/2, I actually get negative 3/2. And then x to the negative 1/2 minus 1, get a common denominator, you should get negative 3/2. That should be it. We can just leave it like that. Negative 1/2, yeah, okay. 20. G of u equals root 2u plus root 3u. Now, there's something subtle here in this problem that they're trying to get you to see. In the first term, root 2u, the u is not underneath the square root. In the second term, root 3u, the u is underneath the root. And so that's going to make a big difference when it comes to taking the derivative. So here's what I'm going to do. First, I'm just going to rewrite this so it's a little easier for you to recognize. Root 2 times u, that's what we got in the first one. Plus, check this out, root 3 times root u. I'm allowed to do that because properties of radicals, if you have a product inside, you can split it up. And that's going to be root 2 times u plus, well, I could have just left it. Let me leave it. Just leave it. I was thinking about what I'm going to do. I'm going to take the derivative. This is a constant times the function. So derivative of this, the constant's going to come. Derivative of u is easy. This is a constant times a function of u. The derivative of that's one of the things I said you need to memorize. I was going to rewrite as u to the half, but that would kind of defeat the whole purpose of me telling you to memorize that. So g prime of u, let's just do this. This comes for the ride, root 2. Derivative of u is the same as saying what's the derivative of x. So that's just 1 plus root 3 comes for the ride. And then the derivative of the square root of something is 1 over 2 times the square root of that something. So derivative of root u is 1 over 2 root u. And the only thing really you could do is like take this root 3 and throw it on top there. Like that, plus that. So we're there. That's it. 21. 21. V equals t squared minus 1 over the 4th root of t cubed. So I do have 2 terms, all right? That's nice. But I'd like them all to be like t to a power. So I'm going to just convert this one over first. This is t squared minus 1 over t to the 3/4 power. That's what this means. It means cube it, but then take the 4th root, so that's 3/4. And then I'm going to bring this up so it's not a fraction and rewrite it as t squared minus t to the negative 3/4. And now I'm ready to take the derivative. So the derivative of v is the derivative of t squared. So 2 drops out, 2t, subtract 1, you get t to the 1st power. Here we have a minus sign. We're going to drop out the exponent, negative 3/4 will be multiplied there. And then t to the negative 3/4 minus 1. So I'll need a common denominator there. I just write 4 over 4. There we go. And so you get 2t plus, because I have negative minus, or minus a negative, which is going to be plus 3/4 t to the negative 7/4. And one other way you could write that would be 2t plus, the 3 is on top, there's a 4 on the bottom, and then this drops down and joins the 4, t to the 7/4. And that's fine. Just keep in mind also, when you have t to the 7/4, this is the same as the 4th root of t to the 7th. And that you could even go further and write t to the 4th times t cubed, because that's t to the 7th. And the reason I did 4 and 3 was because I'm doing 4th root. I could now even split this up into 2 roots. And the 4th root of t to the 4th, that's just going to be t. And then you have this still. So you could even write 2t plus 3 over 4. This is t, then 4th root of t cubed. You could write that. All of these would be okay answers with me. '23. Let me go check. Well, okay, z equals a over y to the 10th plus b cosine y. Now, one very good question you could have here is, what is the independent variable? Is it a, is it b, is it y? So they don't specify it here. Like, to specify it, I would need to write something like z of y, and that would tell you that y is the independent variable. So here's what you need to know. In this book, your most commonly, the variables can be like x, y, even z, r, s, t. But anytime you see like an a, a b, or a c, or a d, or something like that, or capital or lowercase, doesn't matter. Those usually tell you that you're dealing with constants. So this is a constant, this is a constant, they're just not telling you what it is. So it's kind of implied here that y is the variable. All right, so with that in mind, let me first try and rewrite this so that I have y to a power. So a y to the negative 10, I'm bringing this up, okay? And then the other part, I should be okay with taking the derivative. I don't need to do anything to that. So let's look at the derivative. All right, a is a constant. It's attached to the function. It's going to come for the ride. But the negative 10 is going to come out and multiply times this. So I'm going to have negative 10 times that a, then y to the negative 10 subtract 1. So I'm using the power rule there. And then plus b times the function. It'll just come for the ride. But derivative of cosine of y is negative sine y. I'm putting it in parentheses there because that's multiplication, not subtraction. And this can be, oh, I forgot to put prime, sorry. This will be negative 10a y to the negative 11. And then when I put these together, it'll become negative. So I'm going to put minus b sine y. There we go. You could drop that down back below this as a positive 11 power, but I'm just going to leave it. Ooh, 24 is interesting. 24 is interesting because they're using like other letters and it throws people off. Y equals sine theta over 2. And then plus c over theta. All right, here, c is our constant, is a constant. Theta is our variable. Theta is basically like an x. So you're trying to take derivative. You've got two terms. We can do them individually. I'm first going to rewrite this, all right? So look, this right here, although it looks confusing, is really just 1/2 times sine of theta. That's all that is. And then the last part, because theta is my variable, I don't want it down here. I need to bring it up. So this will be c times theta to the negative 1. And now I can differentiate each one. So derivative is, well, what's the 1/2 just going to come for the ride because it's attached to the function. So 1/2 derivative of sine of theta would be cosine of theta. And then plus c, my constant comes for the ride because it's attached to the function. Negative 1 comes out, right? So this negative 1 drops out, multiplies times the c. I'd make it negative c, so let's do that now. And then I get theta, and I subtract 1 from negative 1, I get to the negative 2. And that's it. You could drop the theta back underneath this, the c as a theta squared, but I'll just leave it there. And 26. U equals, I can't even read this. U equals the cube root of t squared plus 2 square roots of t cubed. Now, I'm going to try and rewrite these two terms as powers of t. So the first one is t to the 2/3 plus 2 times this is t to the 3/2. So the power, you can look at it this way. The power is 2, the root is the denominator. Power is 2, root is denominator. Here, power is 3, the square root, there's a 2 out here, is the denominator here. So there's the function. Let's take its derivative. So this is pretty straightforward. 2/3 is going to pop out, 2/3, t to the 2/3 minus 1, plus the 2 that comes along for the ride, but the 3/2 pops out, t to the 3/2 minus 1. This is 2/3 t to the, if you do this subtraction, get a common denominator, negative 1/3. And then when I do this multiplication, the 2's cancel, so I just get plus 3. T, 3/2 minus 1, get a common denominator, you get 1/2. That's it. All right, I'm going to do 27, and then I think I'm going to take a little break. Although you're not going to know, right? The video is just going to skip and then come right back. I had a student point that out to me, which I know, but still. All right, number 27, find the equations of the tangent line and the normal line to the given point. Okay, so let me see if, let me do it this way. All right, so let me put the function up here, the curve, y equals 6 cosine x, and I want to look at the point pi over 3, 3. All right, so if I were to graph this curve, it's a cosine curve, 6 in front is the amplitude, so that means that it's 6 here and negative 6 here. And since it's a cosine curve, it has a period of 2 pi, right? And it starts up here, ends up here, and does something like this. Roughly, okay? Roughly. Now, at pi over 3, if we were to plug pi over 3 into that, we would be at, this is pi over 3. If we plug it in, we get 3. So this is the point pi over 3, 3. What we want to know are two things. What is the equation of this tangent line? And then, what is the equation of what we call the normal line, which will be the line that is perpendicular to the tangent line. So we want the red line's equation, we want the blue line's equation. So let's work on the red line's equation first. Well, I need to know the slope of that line. And the slope of that line requires the derivative. So let me take the derivative quickly. The 6 comes for the ride. Derivative of cosine of x is negative sine x. That negative gets applied to the 6, and we have this. So if I want to know the slope of a tangent line on this curve, right, it comes from this formula. And so the slope, right, of the tangent line at that point requires that I plug in pi over 3 into this. So sine of pi over 3. Now, what is sine of pi over 3? Well, that's why you took pre-cal. So this is going to be -6. Sine of pi over 3 is root 3 over 2. And this just turns out to be, let's see, 6 and that's -3 root 3. Wow, that's a weird slope. Don't use a decimal, okay? We want exact values here. So this is the slope of the tangent line. Look, it's negative. That makes sense, right? I mean, it matches. All right, that gives us just the slope. We want the equation of this line. So this is where we go back to that formula. Y minus y1 equals m times x minus x1. And I know my y1 is 3. My slope I just found, -3 root 3. And then x minus x1, which is pi over 3. I'm not going to solve this for y. I'm just going to leave it like this and box it. That is the equation of that red line. Now, the only difference between the red line and the blue line, right, they both go through the same point. So they both have this as an x1, y1. The only difference is the slope. And remember from college algebra, if you have the slope of a line, if you want to find the slope of a line that's perpendicular, which this one is, the blue one is, all you have to do is use the negative reciprocal of the slope. So that means just take the slope that we have here and do the reciprocal of it and change the sign. So the slope of the blue line, okay, the slope of this blue line is going to be that flipped over, so right is 1 over 3 root 3. It was negative, so now it's going to be positive. Okay, so that is the slope of this blue line. And then all you have to do is just do that equation again. So you have y minus, same y1, so y minus 3 equals this slope instead. And then x minus pi over 3. There you go. That's it. That's the equation of the normal line. This is the equation of the tangent line. Normal line there, tangent line here. Someone might say, hey, you can't leave a root in the denominator. Yes, you can. It's not against the law to do that. If you did rationalize it, though, just so I can make some people happy that don't like that, you would multiply the top and bottom by root 3 here. These two would go together and become a 3, and then I would have a root 3 on top, so it's root 3 over, these two were 3, and then times 3, so that would be 9 down here. So root 3 over 9 would be the same as that, but I'm just going to leave it. All right, let me see what time it is, or how long this video is. Yeah, that's about right. Okay, so quick little break. Find the first and second derivatives of the function. So we're going to have to take two derivatives here. F of x is given to us as x to the fourth minus 3x cubed plus 16x. I want the first and second derivatives. So the first derivative, all right, I can do three different terms. I can do them one at a time. So derivative of this, 4 comes out front, subtract 1 from the power, get that. Here, the 3 drops out front, joins the negative 3, becomes negative 9, multiplying them, right? Reduce the power by 1, I get x squared. Here, the 16's there, but then I have derivative of x, which is just 1, so I get 16. There's my first derivative. Second derivative, I just differentiate this. So 3 terms again. Here, 3 drops down, hits the 4, it becomes a 12x, and then squared, reduce the power by 1. 2 drops out, hits the negative 9, gets negative 18, and then x to the first power, and then derivative of a constant is 0. So that's it. All right, 33. And 32 looks interesting. Maybe I'll do 32 after this. G of t is 2 cosine t minus 3 sine t. All right, the first derivative, 2 terms, so I'm doing one by one. 2 is going to come down. Derivative of cosine t is negative sine t. That's going to change that to a negative 2 sine t. And then here, the minus 3 is going to come down. Derivative of sine of t is cosine t. So I get negative 3 cosine of t. And that's it. I go again. Second derivative. All right, negative 2 is going to come down. Derivative of sine t is cosine t. So I have negative 2 cosine t. And then here, the negative 3 comes down, but the derivative of cosine t is negative sine t. So that negative is going to come out here and change that to a plus 3. And then sine t. That is it. Yeah, and I like 32. Square root r, cube root r. All right, so let's try the first derivative. This one I can do pretty much on the fly because I know the derivative of root r is 1 over 2 root r, but then I'm going to need the derivative again. So I am going to choose here to rewrite this as r to the 1/2 plus r to the 1/3 first. Then when I take my derivative, I'm going to bring the 1/2 out. R, and then I'm going to subtract 1 from 1/2 and get negative 1/2. Here, the 1/3 comes out, so plus 1/3 R, and then I take 1/3 and I subtract 1, which gives me negative 2/3. That's my first derivative. Second one, I drop the negative 1/2 out. It multiplies times 1/2, that's negative 1/4 R, and then I subtract 1 from this again. That'll give me negative 3/2. Then I'm going to do this one. The 1/3 is going to be here, but the negative 2/3 comes out and hits it. That's going to create a negative 2 over 9. And then r, when we subtract 1 from this, we should get negative 5/3. So subtracting 1 from that. That's it. All right, 35. They tell you to find d99 over dx99 of sine x. So this is Leibniz notation, and what it's saying is for us to take the 99th derivative of sine x. So I'm going to take the first derivative, then the second, third, fourth, fifth, sixth, seventh, eighth. I'm going to do it 99 times. You ready? Okay, here we go. I'm just kidding. We're not going to do that. We're going to do it, and then we're going to see what happens here. So let me try it this way. I'm going to write my notation just a little bit different. I'm going to call y equal to sine x, all right? And call it y. That's y. Now, my first derivative is going to be cosine x, because the derivative of sine is cosine. The second derivative is going to be negative sine x, because the derivative of cosine x is negative sine x. The third derivative is, well, that's a negative, so it needs to come, but derivative of sine is cosine, so we get negative cosine x. And then the fourth derivative, which I'm going to write y with a little 4 in parentheses up here, is going to be derivative of this. Now I have a negative there, so let's ignore it for a second. Derivative of cosine x is negative sine x, but then negative, so it's going to be sine x. So I'm on the fourth one. I got a long way to go, right? Well, no. What we notice is that we're back to where we started. We were at sine, right? We're back to sine. So when I do the fifth derivative, it's going to be cosine x. Let me move it down just a little bit so I can line these up. Fifth derivative, right, is going to be cosine x. And I think what I'll do is I'll move this fourth derivative up here. Fourth derivative was sine x. and I'll erase it down here. And then the 6th derivative is going to be negative sine x. So I'm just following this pattern. The 7th derivative, so that's a 7, come on, equals negative cosine x. And now it's going to start over again. The 8th derivative will be sine x. The 9th derivative will be cosine x. The 10th derivative will be negative sine x. And then the 11th derivative will be negative cosine x. And I could keep going until I get to 99, but I'm going to do even better than that. I'm going to notice that if I look at all these, this is the first derivative, right? Second derivative, third derivative. Let's call this the 0th derivative, meaning we didn't take the derivative. That is technically what we do. I'm not just making that up for fun. Okay, this is the 0th derivative. We didn't take derivative. First derivative, we took derivative once. What I'll do is I'll change that prime to a 1 just so you can see this. This one right here was a second derivative, 2. This one was a third. This is 3. All right. So I know that if the derivative I'm taking is 0, 4, 8, the next one would be 12. If the derivative I'm taking is a multiple of 4, then I know the answer is sine. And I ask myself, is 99 a multiple of 4? It is not, so it can't be this. Now how about this one? This row, 1, 5, 9, right? These are all multiples of 4 plus 1, I guess you could say. What would fall in this list? The next one, I'm going to add 4, 13, right? The next one after that, I add 4, would be 17, right? So the question is 99 in this list or not? Maybe, maybe not. How about this list? Could 99 be here? Well, look, 2, 6, 10. Those are all even numbers. There's no way I'm going to have 99 derivatives. So I'm going to eliminate this. I'm going to eliminate this one. It's not going to be those. It's either going to be cosine x or negative cosine x. So we just need to figure out, is it going to land in this list or this list, right? Is 99 in this list or this list? So there's two ways to go about this. You can just list out all the numbers, right? And see if 99 lives here. Or you can go more technical, which is to come up with some sort of formula for this. I think the formula is better for students who are going to go on and do more math. But the list is just as efficient. Well, not as efficient. It's easier, but we still have to count out to 99. And tell you what, if I change this to 999, you sure as heck wouldn't want to make the list, would you? So let's try and come up with a way of representing what the answers are. All right, this is going to look a little confusing. All right, if we take the derivative, right? If we take y and we take the kth derivative, all right? So that k can be 0 or 1 or 2 or 3 or 4 or 5, 6. We know that we're going to get one of 4 answers. We're going to get sine x, or we're going to get cosine x, or we're going to get negative sine x, or we're going to get negative cosine x. Those are the 4 possibilities. We will get sine x if the k power we have here is a multiple of 4, right? So how do I say that? How do I say that if k is a multiple of 4? Well, there's a different way. There's kind of a different way to approach it. We can say all of these numbers, if you divide them by 4, right? If you divide them by 4, you get a nice integer number, right? So if I take 8 and divide it by 4, I get 2, right? 8, that's 8. Divide that by 4, I get 2. And I get no remainder there, right? I know that's old school notation, but there's no remainder. If I take 4 and I divide it by 4, I get 1 and there's no remainder there. If I take 0 and divide it by 4, I get 0. And again, there's nothing left over. However, if you look at like 9, if I take 9 and divide it by 4, I'll do that here. I get, what, 2 goes in there, and then you'd have 8, and then you have 1 left over, right? You would have a remainder of 1. If I take 5 and divide it by 4, it goes in there 1 time, 4, and then look, I have a remainder of 1 again. And if I take 1 and divide it by 4, it doesn't go in there, right? It doesn't go in there. So you could say you just have 1 left over because you started with 1. So the idea here is what's called modular arithmetic, okay, module. If I say something like 9 mod 4, the answer to this is 1. It means if you take 9 and divide it by 4, how much will be left over? 1, a remainder of 1. If I take 5 mod 4, it's also 1. If I take 1 mod 4, it's going to be 1. And what was the next one that would have been in this list? 1, 5, 9, we add 4 to it. So 13 would be in that list. If I take 13 mod 4, right? 13, 4 goes in there 3 times, that's 12, and I have 1 left over. So that would also be 1. So notice that in the first row, if I take this power and I mod it with 4, I have no remainder. On the second row, if I take this power, or not, I said power, sorry. If I take the derivative, okay, the number of the derivative, and mod it with 4, I get a remainder of 1, right? Let's look at the third row and look at the, I'm not going to say powers, I should slap myself for that. Look at the derivative we're taking, and let's see what those are mod 4. And I'll start with 10. What is 10 mod 4? What's 10 mod 4? Well, let's do it. 10 divided by 4 goes in there twice. Goes in there twice. We have 8, and look at the remainder, 2. Let's try the next one, 6. What's 6 mod 4? Well, it goes in there once, that's 4. Look, the remainder is 2. And then what about 2 divided by 4? Well, you can't go in there, so you're just going to be left with 2. So it looks like everything on the third row, if I take that derivative number here, and I mod it with 4, I should get a remainder of 2. And then what about the last row? If you take 11 and mod it with 4, 11 mod 4 goes in there, well, it only goes in there twice, and you have 8, and look, your remainder is 3. And if you try it again with 7, you'll have a remainder of 3, and then here you'll have a remainder of 3. So there's a pattern. Your answer will be this first row if when you take this derivative and mod it with 4, you get 0 as a remainder, or 0. And it'll be cosine x if you take this derivative number, mod it with 4, and get a remainder of 1. It'll be negative sine x if you take this derivative and mod it with 4 and get 2. And this one if you mod it with 4 and get 3. So I'm going to say that over here. It will be sine x if the power, I said it again, dang it, okay, all right, I just slapped myself. K, if the derivative we're taking modded with 4 equals 0. Here, if k mod 4 is 1, we do this, and then k mod 4 is 2 will be negative sine x, and k mod 4 is 3 will be this. Hope that makes sense. So what about 99? If we take the 99 derivative, what I need to figure out is what is 99 mod 4? Well, let's do it. 99, 4. 4 goes into 9, what, twice? That's 80. We subtract, we get 19. 4 goes into 19, what, 4 times? And that's 16, and we have 3 left over. If we have 3 left over, then 99 mod 4 is 3. And that means the answer must be negative cosine x. Now, to illustrate the power of this, if I take now and I ask you what is the, let's say, 2,351st derivative of sine x, then all you'd have to do is figure out what 2,351 mod 4 is. So you'd go and 2,351 mod 4, let's see, this can take me a while. Goes in there, let's see, 5, that's 20, that's 351, and then 4 goes in there, what, 8 times? 8, 32, something like that. 130, 147, 728. Hey, I think I'm getting 3 again, mod 3. 2351 mod 4 is 3 again. So quick arithmetic. I'm going to double check this. I want to make sure. Can't believe I'm checking division right now, but 587. Yeah, okay, that was right. So the answer to this would also be negative cosine x. Just happened to be that way. All right, so that's better than having to count, like go through and find a pattern and count yourself out to that number. That would take forever. So. All right, very, very nice problem. Imagine you could do this with cosine x too, right? What's the derivative, the 99th derivative of cosine x? You would see a pattern again. You would see it start repeating itself at some point, but it would be different than this. You would have to actually work through it. I hope that mod thing makes sense. Modular arithmetic. We're just concerned about the remainder. $37. All right, for what values of x? Okay, so where on this graph do we have a horizontal tangent line? So let's translate that. Horizontal tangent line means that the slope of the tangent line is 0. But for us, that means the derivative is 0. Right? So to have a horizontal line, it has to be like this. The slope has to be 0. We want the tangent line to have that slope. And the tangent line, the slope of tangent line, is the derivative of the function. So we're basically saying we need to take the derivative of that function and set it equal to 0. And then solve for x. So let's take the derivative first. Derivative of x is 1 plus 2 comes along, derivative of sine x is cosine x. So 2 cosine x. And now what I'm going to do is I'm going to take that derivative, I'm going to set it to 0. So that means we get 1 plus 2 cosine x equals 0. Oh yes, here comes pre-cal. This is a trigonometric equation and we need to solve. So I'm going to try and solve for x here. I'm going to first move the 1 over. 2 cosine x equals negative 1. And then I'll divide both sides by 2. Now, the question is, where on the cosine function are we getting a value of negative 1/2? Now, you could go look at the graph of the cosine function, but I hope that your experience with pre-cal was tied or connected more to the unit circle, which is where I go whenever I'm trying to solve these. So I go back to my unit circle. I just remember that if someone gives me an angle, right, that the x-coordinate of that at that angle is cosine of the angle. So like if someone gives me an angle here, theta, then this point right here is cosine theta sine theta. And so when we're asking ourselves, when is cosine of x equal to 1/2, we're really saying, this is like the angle, okay? We're really saying, like from pre-cal, where is cosine theta equal to negative 1/2? At what angles are your x coordinates negative 1/2? And you have to remember all the different values on the unit circle, and hopefully you'll recall that your x coordinate will be negative 1/2 up here and down here. So let's determine what those angles are. This one right here is the angle 2 pi over 3. And see, 4 pi over 3. Okay, those are your two angles. Now, you should also remember from pre-cal that if you're not given a restriction on where to look, okay, which we are not here, we have to have a general solution which includes all the infinite number of angles that would get you to that point. So, you know, you could have this angle 2 pi over 3, but you could also have gone all the way around once and then added 2 pi over 3, or you could have gone all the way around twice and then added 2 pi over 3, or you could have gone backwards, right? So the way we get all answers is to say, 2 pi over 3 plus 2 pi, and depending on your instructor, you either use k or n. Doesn't matter, I'll use k, fine. I might even use n in class. So this basically says, look, I can go to this angle and I can add a full rotation and be right back to it, right? Adding 2 pi is a full rotation. K tells you how many rotations. So you could add no rotations, you would be here. You could add 1 rotation, or 2, or 3, and that would take care of all infinite number of answers. And then same thing with this one. Start there, add 2 pi k. So we have this as our solution, all right? X has to be equal to any of those infinitely many answers. And I guarantee you that if you go to any of those values on this trig function, f, this one right here. So if you plug in anything from here into here, I promise you, you're going to have a horizontal tangent line there, flat. Or sorry, 38. I think 38 is a little easier than this one because it doesn't require any trig. So I'll just give you a hint on 38. It's the same exact question, so you have to take the derivative and set it equal to 0. When you take the derivative of that, you're going to get a quadratic. And to set a quadratic equal to 0, you can use a quadratic formula. If need be, you might be able to factor it. Look at 39 though, 39. It gives you a curve y equals 6 x cubed plus 5x minus 3. So it gives you this cubic function. And it says show that this curve has no tangent line with a slope of 4. So if I graph this curve, it's going to look like something, whatever, all right? I'm not even going to try and draw it. It's there, right? What we're trying to say is there's nowhere on this curve where if you go out to a point, you would have a slope of 4. So I can give you an example. Let's say I have a curve that does this, okay? If I go to any point here, notice that the slope of the tangent line is always negative. There's no way I could ever have a slope of 4 here. They're trying to get us to say the same thing here. Prove to me that that can't possibly have a slope of 4. So here's what that translates into. Okay, show that the slope of the tangent line cannot ever be equal to 4, which means show that the derivative can never be 4. So let's take the derivative first. What is the derivative of this function? 18x squared plus 5, all right? That's just clean derivative. Now, let's try and figure out if this could ever be 4. Question, is it possible for me to plug in an x and get 4? All right, let's start moving things around. So 18x squared, let's subtract 5 from both sides, we get -1. I'm already done right now, I can tell you no. Let me divide by 18. Now, why isn't this ever going to happen? Well, no matter what x I ever pick, if I square it, it can't be negative. So this is never going to happen, which means that's never going to happen, that's never going to happen, and so we're done. Okay, you can just say, hey, look, that's not happening. All right, number 42. Where does the normal line to the parabola blah blah blah? Okay, let me write this down. Where does the normal line to the parabola y equals x minus x squared at the point 1, 1, or 1, 0 intersect the parabola a second time? All right, so we have a parabola, and I'm going to try and graph this just to give us an idea what's going on here. Let me graph it by just a real rudimentary graph. I'm just going to try and figure out what the x-intercepts are real quick. I just set the function equal to 0, factor out an x. So I have 2 x-intercepts. One of them is at 0, one of them is at 1. And I know it opens down, so it goes like this. All right, so it says, here we go. We got this parabola, and it says, where does the normal line to the parabola at the point 1, 0? So here's the point 1, 0, right? So I come here. I have obviously a tangent line through here, but I also have a normal line which runs perpendicular to it. This. It says, where does that normal line intersect the parabola at a second point? We want to know what that point is. Where is that point? Okay, well, you can make this really difficult, or you can make this a little easier if you just think about what's being asked, all right? If somebody gives you 2 functions, there, 2 functions, and they want to know where they intersect, so let's say this function is f and this function is g. If I want to know where these 2 hit each other, then I would set the functions equal to each other, and I would solve. And wherever these 2 were equal would correspond to the x values for those intersection points. Same thing here. I have a parabola. There it is. Boom. And I want to know where that intersects this line. Well, I don't have the equation of that line yet. And that's what I'm going to go find. As soon as I know the equation of this line, then I'm just going to set this line equal to that parabola, and I'll get the points. That's it. So really, we're just finding the equation of the normal line first. So how do I find the equation of this normal line? First, I'm going to find the slope of the tangent line. Then I'm going to take the negative reciprocal of it to get the slope of the normal line. So start with the derivative. Derivative of this is 1 minus 2x. Now, I want the slope of this tangent line, the red one, the slope of the tangent line, let me draw the tangent line in here. The slope of the tangent line at this point 1, 0. So to do that, I need to plug 1 into the derivative to figure out what the slope is. So the slope of the tangent line is going to be 1 plugged into this, so 1 minus 2 times 1. This is -1. But that's not the slope I want. I want the slope of the normal line. And the slope of the normal line is going to be the negative reciprocal of that. So if I look at the negative reciprocal of this, I just take it as a fraction, I flip it over, which is still -1, but I change the sign, which means +1. So the slope of the normal line is +1. So now let's write the equation of the normal line. So I write y minus y1 equals m times x minus x1. And the point here is 1, 0, so y minus 0 equals m, the slope which was 1, and then x minus 1 plugging in here. And clean that up, and you just get y equals x minus 1. That is the equation of the normal line. There it is. That red line, that's its equation. Now, where does it hit the parabola? Well, I know for sure it hits it here, right? I already knew that, but I need to find the second one. So I'm going to take this equation right here, right, and set it equal to that one. Since they're both equal to y, set them equal. So I'm going to do x minus x squared must equal x minus 1. And this is going to be pretty nice. The x's cancel on both sides. And I get negative x squared equals negative 1. I'll divide both sides by negative 1. You get that, and then I'll take the square root on both sides. And anytime we take the square root, we have to do plus or minus. So our two answers are plus and minus 1. Now, I already knew that. I knew half of that. I knew that if I plug in 1, right, I'm going to get 0, and that's one place they hit. The other place they hit is at negative 1. Okay, so I know if I plug in negative 1, I should also, it should be on both curves. So let's just check it. If I plug negative 1 in here, negative 1 minus negative 1 squared, what do we get? Negative 1 squared is 1, but then we subtract it, so that's minus 1 again. This is negative 2. I get negative 2 if I plug it in here. But I should get the same thing here. So if I plug negative 1 in here, I get negative 1 minus 1 is negative 2. So you can see that this point, negative 1, negative 2, lives on both curves, right? Both curves. And it represents where this normal line, the other point where this normal line intersects the curve. That's it. That's a really good problem. All right, I believe this will be the last one I do. We're gonna skip number 53. We're gonna not do it. All right, so don't worry about 53. We will address that problem later, just not now. It will come up in a different section. 43. All right, equation of motion of a particle is s equals t cubed minus 3t. So this represents the motion of a particle. So we've got I'm already thinking distance and time. Where s is in meters, okay, s is in meters, and time is in seconds. A, find the velocity and acceleration as functions. So for part A, the velocity is equal to the first derivative. This is what we learned in class. So just take the derivative, 3t squared minus 3. I hope by this point in time you can do that mentally. And then the acceleration function would be the derivative of that, which would just be 6t. That's it, first part. Part B, find the acceleration after 2 seconds. So for part B, we want this acceleration at 2 seconds. So basically, I'm taking 2 and plugging it in. Almost look at this as like a function. A of t, well it is, but let's write it with different notation. V of t equals 3t squared minus 3. So for part B, they want to know A of 2. Plug 2 into there, you get 12. 12 what though? Well, acceleration is going to be in meters per second, which is your velocity per second, right? So 12 meters per second, or you can say meters per second squared. And I talked about this in class, how when you go from distance, time, and then you take the derivative, you got velocity, time, and then you take the derivative again, you got acceleration, time, like this. That if this is meters in seconds, then your velocity up here becomes meters. I'm going to say meters per second. Right? So it's whatever this unit is divided by this unit is what the velocity is. And then when you do acceleration, it's going to be this unit over this unit. So you're going to have meters per second, but since time is seconds, again, you get that. So that's it. And then C, the acceleration. Oh, find the acceleration when the velocity is 0. That's more interesting. What's the acceleration when the velocity is 0? Well, first thing I need to do is figure out when is the velocity function 0? When does that happen? So I take my velocity function, right, here it is, velocity function, and set it equal to 0, and you should get two solutions, plus or minus 1. We're going to assume here that time can't be negative, all right? Just, it makes sense. So you should get just t is 1. So this doesn't answer the question. It says find the acceleration when the velocity is 0. The velocity is 0 when t is 1. So to know what the acceleration is at that point, all you have to do, point in time, is to just plug that result 1 into the acceleration function, which would be 6 times 1, which would be 6 meters per second squared. There we go. I've had students in the past ask me why meters per second is meters squared. If you have meters per second, you can rewrite this bottom s as s over 1, and then you can flip up 1 over s like that, and it's gone, and then you go across, and that's where you get meters per second. All right, I am done with this section, which is great. There's a lot here, so I'm happy.